Hi, thank you for joining in. We will take 2 more minutes for other participants to join in, and then we will begin the webinar. Okay, good morning, everyone. I welcome you all to the fifth webinar of Simulations with Design Builder webinar series. And this is the last simulation webinar for 2021-22 challenge. I am Amanda and I will be moderating today's session. In this webinar, we will see how to incorporate your solar PV system in Design Builder and analyze the data. We will also touch upon the topics from the previous webinar about modeling a centralized system for energy efficiency. Next slide, please. Before we begin, I would like to thank our program supporters and affiliates for this year. These organizations have provided immense support to Solar Decathlon India and catalyzed our transition to a net zero future. Today, we have with us PC Thomas. PC Thomas is the founding director of Team Catalyst and also an adjunct associate professor at University of Sydney. He specializes in integrated building design using simulation tools to assist in the design and delivery of sustainable buildings, in particular in predicting the performance of mechanical services. He has a master's degree in mechanical engineering, 30 years of consulting, research, and teaching experience in sustainable buildings, building energy simulations, energy auditing, energy efficiency in buildings, and solar energy. So, hi, PC.
Hi Amanda, how are you?
Thank you, PC, for joining. So, before we begin with PC's presentation, I would like to mention to all the participants here, please feel free to send in your questions anytime during the session. We will take them as many questions as time allows during the session. And with that, let's get started. So over to you, PC.
Thanks Amanda. So guys, what I thought we might do is we can look briefly at how solar PV systems are integrated into a design builder model. It's not very difficult and we have some resources for you. Amanda will share a PDF tip sheet, and I've also provided a link to somebody who has put together a series of 3 videos where he looks very carefully at how to put together a PV system in Design Builder. But in the meanwhile, I'll show you a very simple version of what I've done, so at least you know how to get started. And then um, if that's okay, we can take another session at the centralized air conditioning system. There were a number of people who were there last time who were interested. If you guys are still there, we can do a little bit of um, detailed HVAC system modeling. Okay. So, Amanda, can I share my screen?
Yes, PC. Yeah, you can share your screen.
Okay, so just let me know when you can see my screen.
We can see it right now.
Yeah. So Amanda's just provided the tip sheet that you can look at, and that's what the tip sheet looks like. So what we've done is, we've showed you how to add a solar collector array to a building model in Design Builder, and then to connect it to an electric generation or distribution center in the building, which will then either feed the building or the grid. Okay, and essentially allows you to specify, select the storage options, types of inverters, PV system with efficiencies, etc. And then we can run a simulation and then see how the PV generation works. So there's a very simple diagram here. I'm sure all of you already understand how PV system works. The only thing we're trying to show you is how the connections happen within DesignBuilder to make this work. So you're given steps, okay? So at the building level, you have a generation tab. You can include electric centers. So if you go to the model at the building level, on the generation tab, I have selected a load center, a DC with inverter, right? And then once you've done that, you can draw a PV system, and you can go to the layout tab, and if you look here, that's the solar collector module. So what I've done is I've just drawn a solar collector over here. Now um, if I edit that, then that will actually give me what kind of solar collector I've got, what's the efficiency, how is it connected, etc., etc., etc. And on the tip sheet we've given you, those things have been mentioned. So step 2, what to do to draw the solar collector. Step 3, how to connect it, size it, right? And step 4, connect it to that load generations center that we have just specified. Okay. And once you've done that, when you run the energy simulation, and I think I've already run a simulation, let me just check, otherwise we can run it again. Then under the HTML report that you normally see, and I'll show you that. Okay, I'll just run it again. Yeah. So under the HTML output, within that file, you will find that there is a whole section on electric generation, and you'll find all the data there. So it comes under this section called electric loads satisfied. Okay, so let it just finish. It's going pretty quick. I don't even need to load the results. I can simply, okay, I'll open this up. But essentially, I'm just picking up the HTML file. Okay, so you can see it here. Okay, let it be there. So on the top, where we've seen this before, no difference. These are the end users by subcategory. If you go down just a little bit more, you'll see this electric load satisfied. And here you'll see photovoltaic power, how much of the building load it has supplied, and what the total on-site electric resources are. So all of that data for the PV system will come in over here. And then if you look, once you've got the basic system working correctly, if you watch some of the other YouTube tutorial link that Amanda has provided, let me just pull that across for you here. Amanda, can I share with sound?
Yes, you should be able to.
Oh yeah, yes.
Yeah?
Yeah.
Okay.
So I will share sound. Okay. So this guy has actually put a 3-part tutorial. I've given you the link for that. And he actually goes through.
Everyone, this is Ömer Karagüzel.
in some
And
detail.
welcome to another tutorial of
He goes through in quite a lot of detail on how to uh, put solar PVs on Design Builder, and he's actually, I think he works in the solar PV industry, so he's got quite some knowledge about it, and he has given
you.
quite a nice.
As you know, solar PV modules are
So he shows you how to look at an actual PV system technical data sheet, take those technical data, so you're modeling the PV system of your choice, and then input into Design Builder and work out how to integrate those outputs. Okay, so not very difficult, but a little bit of detail. You have to spend some time on it, understand what are the data to put in. Some of the defaults are quite maybe not as efficient as the panels that you're getting nowadays. So it's better to work through this tutorial where he's actually looking at a couple of real products and putting those onto Design Builder. Okay, so I encourage you to try. I don't think you'll face too much trouble between the tip sheets that I've given you and this tutorial that if you can watch, it won't be very difficult to do the, the PV system. Obviously, depending on the orientation and the tilt, the output will vary, and that the Design Builder model will work out for you, and you need to give it all the efficiencies and the losses and all those bits and pieces in describing the model. So I don't think it's really worth my giving you any more um, instruction on that. I think it'll be very easy for you to work that out on your own. If there are any particular questions, I can deal with that right now. So I'll just look up the chat box to see if there's anybody asking for. Okay, so I think the tip sheet and the YouTube link are both in the chat box. There was somebody asking for that, so please pick it up from there.
PC, I have a couple of questions I'd like to ask. Maybe it'll help the participants.
Please.
Yeah. One is related to the models, PV models, the various models that are available. Is there like a database of various models available, or are we expecting the students to sort of put in the information? And if that's the case, any tips on, should they work with manufacturers, etc., to get that information?
I think the models that are included, from what I've when I've spoken to people who have used it, who know about these things, they were saying that some of the models were a little bit too simplified and the losses were too high. So in one sense, it gives you a conservative prediction, but maybe you don't want to be that conservative. The module performances and the inverter performance over the last 2 to 5 years have changed quite a lot, and they are not, I would say, properly reflected in the models. You can build your own models. So like in everything else under Design Builder, you have the option of providing your own data sheets, right? So I'm showing you some areas, but obviously there's more to it than that. If you go to each of the parts in the data, you can really work out what can be put there. It's again, as I said, it's not very complex. It's more working through the process to make sure that you have put everything in correctly, and the model will start working pretty much as soon as you draw the PV system and you connect the electrical load centers. then it's really a matter of you finding technical data to input your selected PV module and your selected inverter with the efficiencies and so on. You don't really, I think where we are at, we're not trying to work out the best PV system possible. We're trying to work out how does it marry with the building loads. And I think that's more important to do. So even keeping the PV system relatively simplistic will be fine because it's working out every hour what's the load. It's looking at what's the load that the energy simulation program is predicting from the building, and then it's working out, how much of the load of the building is being satisfied by the PV. And that's probably the critical part of what needs to be done for the SDI competition.
And then the rest is considered to be exported on a net metering system.
You can do that, yes. It'll tell you how much is used on site. So obviously the rest is exported or wasted.
Okay.
But
So yeah, I
exported.
guess that was going to be my other question, because one of the things that we are asking the students is to plan for, in the resilience contest, to plan for a few days of autonomy of the building based on battery storage.
Yeah.
And so is that something that they can incorporate in here?
Okay. A battery storage I haven't really looked at
Okay.
in some detail.
Okay.
I have a feeling that the YouTube guy who has done it in 3 parts has actually looked at it. I'm not sure,
Sure.
but that's something that I can find out because
Okay.
typically I don't do a lot of work in that area. I haven't really looked at that.
Okay.
I suspect it should be possible, but this is okay because at this point it's only looking at what is the power generated from the PV, what's the conversion factor, what's coming from the utility, here's the export going to the utility, and so on and so forth. So
Sure.
you can work that out. I haven't looked at the battery storage aspect as yet.
Okay.
That's a very obvious question. Sorry, I'll try and find out some more detail about that.
Okay.
PC, I have a question.
Sure.
Might not be relevant for the competition, but just a curious question. So, in case if you want to, distribute the load through PV systems and the raw power, is that possible to design in Design Builder as well? Like you want to partly, distribute the load using the solar PV system.
When you say distribute the load, do you mean to particular end users, or how did you mean distribute that load? Like, did
Yeah,
you want it
particular
to be,
to
sorry,
the
go
end
ahead.
users. Yeah, particularly to the end users. Yes.
Okay, there may be some option on that because from what I understand is you can actually select where that load is being put to. I think at this point we were just kind of saying, okay, do it to the base building system. So when you do that, okay, here you have an option to do base load, but you have some options here. Okay,
Right.
they are, you can track the demand limit or track the electrical or go to a particular schedule. I'm not sure you can assign it to a certain load. It just looks at what the building needs and this is what I'm producing and therefore I'll give the building so
Okay.
much.
Okay. All right. Yeah.
Uh, you do get you do get fairly sophisticated in what you can do with the different systems once you start playing around with it. Initially, my advice is just start getting it working. Once the numbers start to come out and they look reasonable, then you try and update the
Right.
PV system type and the PV system efficiency and the inverter efficiency and all those things. Like in any other system, like when you're doing HVAC, same sort of deal. Okay.
We also have questions in the Q&A box.
Okay. Okay, so yes, the first question about do you only have to put it on the roof? No, I think you can, as long as you can draw it on that surface, I think it allows you to do that. You can certainly put it on tilted roofs, and I personally haven't tried it on facades, but I don't see any reason why it can't be. So it's same way of drawing the at the building level. I think if you pick the solar collector and then you try to draw it, I don't think there'll be any. Just hold the shift key down and you should be able to draw uh, a PV panel anywhere. I think it won't draw it here because there's a window here.
Right.
But oh yeah, there it is. So you can draw PV systems on the facades as well. Okay. Can we model a PV system with a part of it having panels all over the site area? Yes, again, I think you can. At the building level, I think if you pick the solar system and you can, in fact, in that YouTube tutorial, I've seen that he does something similar to that. You can draw a panel. Uh, so and then you can even tilt it after you've drawn it. So you can have a whole series of tilted panels providing input to the building. You just have to give it the correct generation name, generator system type, and all that. So I don't think that should be a problem. Okay. And the last question, how to mold the building shading of two towers? I'm not sure I understand that question. Could you repeat that a little bit more clearly? Is it that you're asking that if you've got a shading device between two towers and you want to make that PV system? Yes, you can. You simply draw the PV, like what I've drawn here. You can move those around. So once you've got it drawn, you can move it anywhere you want on the model. So once you can draw yourself some construction lines and just make sure that you can fix it to, yeah. So there's a shading device which is really a solar system, and you can do that between towers or wherever you want. There's no.
You see, I think a related question, or maybe this is also what Professor Gunjan Kumar was trying to ask, is if you have other buildings around the site and you want to model their impact in terms of its shading
Yeah,
on your PV system,
yeah.
how does one do that?
That will, you see, if you have another, let me draw. So suppose I draw, where am I? Okay, so this is on the east side. Let me do one thing. If I make this, say, 10 meters, and then let me make this a component block. So if I then draw, okay, that might be too far away, but let's see. So what you can do is you can check uh, how the sun path works on this one. I might need to bring it a bit closer. So let me say 21st of the month. And really it would be in December and possibly in the morning. Right, so now this part of this system is shaded. The part shading, I think you need to be a little bit careful about. You might need to describe that as not just one array, but a number of arrays. But it will certainly account for the shading on the PV itself from any other shading surrounding buildings. That it will do, because it's working out hourly the amount of solar radiation falling on each plane, and it will certainly be able to do that. It's the characteristics of the solar array that you need to be little careful about. I think if I'm not wrong, on that video that I shared with you guys, I remember seeing that he's actually got a series of arrays that he's placing one beside the other. He's not using any shading, but you can do that, and then you'll be able to account for that. Also, the output from the solar PV solar system, you can look at it on the hourly outputs. So you can see every hour how the outputs are varying. And I would suggest you pick a couple of hours that you know the array is shaded, and then you look at the output before it's shaded and after it's shaded, and it should really be able to show you what's happening there. That's what the model's designed to do anyway. Any other questions?
I think that was the last question, PC, yeah. So.
Okay. So yeah, do have a go at it. I suspect you guys will find it pretty simple to do. Once you've got the basic model running, then it's just if you want to get your typical, your specific PV system inserted, you won't find it very difficult to do. Okay. Now, I'd like to get on to the detailed HVAC system.
So PC, before we move to the next topic, just one more question. Does DesignBuilder also allow to model like solar hot water system?
Yes, it does. Yes. In fact, when you draw that, if you saw, it'll actually allow me to select. It'll ask me, do I want a thermal system or do I want an electrical system? So when I'm drawing here, I can add a hot water collector there. Okay. So it knows which one is which. And then you can connect the hot water system to a domestic hot water system. In fact, if you go to, I'll just escape out of that. You have to do a detailed system, but if you, let me just open that up. So here's my detailed air conditioning system. And if you go to the HVAC system, okay, and if you pick one of the templates, you will find that there is a domestic hot water system, and there will be a solar assisted domestic hot water system. So here's your solar system array, and then there's a couple of storage tanks and controllers and a supplementary boiler, which of course you can delete if you don't have that.
Right.
And in this case, I think it is showing that it is looking after a in-slab heating system to heat the floor, but it can also do hot water systems. So that's all available to there, and you can look up the help file. And I think there's some tutorials online to do that as well. So that's possible, yeah.
Yeah, thanks.
I actually, before I started on the HVAC, I wanted to ask how many people here were really interested in that. Can you put on the chat or the thing that you would like to see that, the detailed HVAC? Okay, there's something in the chat. Okay, so there is some interest. Thank you for that. So this morning I drew up a very simple model, and what we'll do is we'll go from scratch. Like last time, I think it was a bit of a rush job. but we'll try and do at least half an hour, 40 minutes, so you can at least see how to put it together. Now, the reason I decided to do it again is because there are quite a few controls that if you don't get them right, then the output that you get may not be very accurate. So we'll try and sort of work through that. I'll show you one level, and then you'll have to do similar things in all the other levels. With things like PV systems, you will get answers pretty reasonably, even if they are conservative. With things like air conditioning systems, you will get the reverse. So if you haven't done it correctly, you'll get fairly optimistic answers, and which may not really happen in practice. So that's why I was a little keen to work on that. So last time, if you go back and review what we discussed last time, I kind of showed you how to set up a model, do load calculations, assign different zones to different HVAC systems. And we were doing all of that in the sort of simple, ideal HVAC system. Okay. So in this case, I'm going to start from scratch. So what I'll do initially is I'll remove this system altogether, so you can see where we can go from the beginning. So essentially, if it's on simple, you'll find, as I said to you before, on this building data tree, you won't see this HVAC system item. Okay, that item will only come when you turn on detailed HVAC. So the only thing that I would suggest you do is, before you go there, you can ensure that on the simple HVAC you pick a template that matches with what you're going to do in the detailed HVAC system. So what I've done is I've chosen here a VAV air-cooled chiller, air-cooled chiller with reheat sort of thing. There are other options here as well, and I don't have a water-cooled chiller with a sort of simple option. I've got some really complicated options here, so I haven't really bothered to do that. Okay, as long as I know that I've got a VAV system, I've got a chiller plant, and the VAV has got reheat on it. This air-cooled part and water-cooled part changes the efficiency of the chiller, but it doesn't change the connections that we need to do for the simple part. And you can see that at the air-cooled chiller part, if I look at this cooling side, the system COP is quite low. Now, we don't need to worry about that, because when we are modeling the detailed system, it will pick all the component efficiencies from the detailed part. This the simple HVAC tab really will specify what is the minimum outside air that we are putting into each zone, what's the schedule, and then for sizing, when it runs the sizing requirement. Okay. Some other things to be aware of is you should make sure that your supply air conditions for both are keyed to the supply air conditions for the detailed design, because when it sizes and then it runs it, then you want you want to ensure that they are the same type. Okay, so if you have a mechanical engineer on team, it's worth asking them the question, hey, what is a proper supply air temperature for cooling in this climate for this kind of system, and they may give you that. So in this case, what I've got here is 12 degrees supply and 9 grams per kilogram of dry air as a target for supply air conditioning. So the 12 degrees is the temperature, the 9 grams of dry air per kilogram of dry air, 9 grams of moisture per kilogram of dry air is a humidity selection. If you go and look on a psychometric chart, you can find that point. Okay, on the right hand side of the psychometric chart, you have absolute humidity, which is grams per gram. So now what I'll do is I will turn on this detailed HVAC system. So I'm going to turn that from simple to detail, but I'm going to leave the simple HVAC data on. You can make it detailed, but my recommendation is in the first phase, maybe you leave it as simple, understand how the model is running. Then if you have some specific control requirements that the simple HVAC data, when you're using the detailed model, is not enough, then you can turn on detailed HVAC data here. And if I'm speaking Greek, it's all documented quite clearly in the help file. If you start to read it, it should become quite clear. Okay. In fact, on the right hand side in the tip sheet, it already sort of tells you what is meant by the simple HVAC data and what is meant by the detailed HVAC data, which bits are taken for each of those configurations. Okay, so going from there, I will say OK, and as you saw, we've got this HVAC system, but I'm going to start from scratch. Okay, so I'm going to load the template. So the template I want is a VAV system, water-cooled chiller. So I'll go looking for that. So here it is, a VAV with reheat with a water-cooled chiller. So that's my starting point. Okay. And for example, if you don't use reheat in India, you can delete the reheat part and delete the boiler part and so on. But it's best to pick some template and then go from there. So that's the template I've picked. I'll go OK there. And you can see what the template is giving me. It's giving me one chiller, pump, controller, and then one cooling tower. So that's the water cooled chiller. The cooling tower is cooling this chiller. There's a pump for condenser water. There's a set point manager for the condenser water flow and temperature there. There's a boiler, a pump, and a set point manager. Again, same sort of issue. And what we can see is that from the chiller, where you get chilled water, it's connected to the cooling coil in the air handling unit. And from the boiler, you get hot water, that's connected to the cooling coil in the air handling unit, and it's connected to the heating coil in the reheat coil of the VAV terminal in each zone. Okay. So at this point, one chiller, one air handling unit, one cooling tower, one boiler, one zone group. So all the zones are in a single zone group. They're all being dealt by one air handling unit. Okay. So I say next, and I allow all the zones to be conditioned by that single air handling unit. It's not the most efficient of designs, but you can start with that. Finish that off. It will overwrite any existing air conditioning systems and you will get a system. Right? Now, if I run a simulation, it will work because while it's not the most efficient of systems, it's connected correctly. Right? So we don't know yet what the conditions are, but it will run. So I'm going to test that just to make sure that everything is connected correctly. I'll just run say a month. I know that in Delhi, June, July, all these are very hot months. So I can even just run it for a summer design week. So it will look up the weather file, pick out what's the sort of hottest week, run it. I'm just going to ask for monthly and hourly data, so I'll remove the daily data and then just run it. So that will tell me whether the model is working at that point. And I suggest that when you start using DesignBuilder, you save the model before you make a big change. Then you can do, if you want, a save as a different model, make those big changes, test it out at every step to make sure it's working, so that if you make a mistake and something goes wrong, you can step back one step and you can go forward from there. Okay. Now, if you ask me why would a model fail, well, it's very powerful, it's very flexible. It allows you to do lots of connections, and sometimes if you do a connection that is not really something that's useful, then it will give you some, then the model doesn't converge, and then it will give you an error. Okay. So I know it worked. If I lift up the results, I can pick the results here. Summary sheet will give you now on those end users, you will start to see numbers come through. So for that design week, the chiller used so much electricity, the fans used so much electricity, the pumps did this much, the heat rejection did this much. Okay. I'm still not sure whether this is appropriate, but I know the model works. So now I'm going to start looking at some numbers. Okay. We'll look at the chilled water loop first, make sure everything is working the way we would like it to work. Then we'll make some changes. Okay. So I'll close that off and go to edit. And I'm going to start with the loop level. So I'm going to look at the chilled water loop. And if you look at the loop, in Energy Plus, all the HVAC loops are always given to you as a demand side loop and a supply side loop. And there's no different for the chilled water loop. If you open up the cross on the side, you will see that. Okay. So what is what? Well, the cooling coil in the room, in the zone group. So in each zone, when you say zone group, it's got the same kind of zone type for all the zone groups which are being supplied by the AHU. So this one AHU coil is demanding chilled water for the whole building, right? And this chiller, this pump, and this manager, Setpoint manager or controller, is delivering or supplying chilled water to the field, to the building. Okay. Now we need to start looking at it at the loop level. So if you look at the loop level, and if you edit the data, we just want to check that the assumptions, default assumptions, are something that we can work with. Now, as I look at it, the first thing I see is that the loop fluid is ethylene glycol. Now, in the UK, that's quite common because they have negative temperatures, and if you use just water, there's a danger of it freezing. Typically in India, we never do that. We just use water. So I'm going to change the fluid used in the loop to water. Now, you may or may not have variable flow. Okay, modern chillers allow you to do variable flow. Older chillers don't. So you may want to talk to your designer about it. For the present, I'll leave it at variable flow, but it's quite okay to put constant flow. That's perfectly acceptable option. And when I look down here, I see another thing that's a bit of an issue, and that is the loop exit temperature is 6 degrees. That's fine. But then the delta T for the loop is 4 degrees. Now again, typically in places like India and in Australia, we have a lot of cooling requirement, and we do like a higher delta T for our design loops. Now, very typical loop structure is 612. So 6 degrees exiting, 12 degrees coming back from the building when it's at full capacity. So this one I'm going to have to change to 6 degrees. So 6 plus 6 is 12. Okay, so a 6 degree exit temperature and a 6 degree delta T loop. That's what I'm looking for. Now, when is this chill water loop available? So that if there's a demand for cooling, it can work. If you are in an office building, you will switch off the system at the end of the day and go home, start it up again in the morning. So this on 24/7 is not useful. If you're in a hotel, a hospital, something that does work 24/7, then you may want to leave this on. Okay. So maybe I'll change this to, it's best to write your own schedule, but because we're in a bit of a hurry, I'll pick something that's already there. I think there's a Monday to, here we go. So there's a 7 to 6 p.m. Monday to Friday. There's an 8 to 6 p.m. Monday to Saturday. You can pick something. So I'll pick the 8 o'clock to 6 o'clock Monday to Saturday. So my chiller plant is available to provide chilled water during these times. Okay. So at this point I've done that. There is a plant equipment operation part, and right now I'm going to leave it there because I've only got one chiller. Now when I have a second chiller, I need to do some changes to that. I need to tell it how to run the two chillers. Okay. So we'll leave it there. I'll just make sure I've saved those changes. I went cancel on it. So I should have saved it instead of cancelling it. Sorry. So 6 water and the Monday to Saturday 8 to 16. So you need to be quite careful and be mindful about what, wrong one again. Yeah, Monday to Saturday is what I wanted. There we go. Okay, now it's picked up those changes. Okay. Now, what I wanted to show you is how to put a twin chiller plant, because typically when you're using centralized systems, you have a multiple chiller plant room. If you have only one chiller, generally you haven't got to a size where that is efficient. When you get to 1,000, 2,000 kilowatts requirement, then you need multiple chillers. So first I'll just check what is the description for the chiller itself, and I just want to edit that chiller and see that everything is appropriate. Then what I can do is I can clone it, so then it carries over all the settings that I've already got. So now I'm going to edit the chiller object, and this is the default chiller object that comes in DesignBuilder. It's a default chiller object from Energy Plus. It's actually a pretty good chiller object. It's what we call a EIR chiller, energy input ratio chiller, electric EIR chiller. That's got a fairly decent efficiency set of curves. If you don't have any further details, that's not a bad chiller to use. Okay. So at design condition, your reference COP is 5.5. Again, quite a good chiller. The most modern chillers now, you can get reference design conditions 6 and a little bit above. Anything much beyond 6 I'd be rather suspicious of, particularly in the design conditions we have in India. And this sizing factor is important. If there's one chiller, then you want the sizing factor to be 1. So it'll size a chiller for the entire load. If you have 2 chillers, then you might say that one is 40% of the total capacity and the other is 60% of the total capacity. So, then you can start to play with these things. I would suggest leave all these alone. They're all pretty good. And then the curves for the chiller part load operation are here. You can view that. Again, if you don't have much detailed data on the chillers, this is not a bad chiller to use. But if you have some specific chiller that is really highly efficient, you may need to read through the literature and figure out how to provide a new set of curves for the chiller operation. So there are 3 sets of curves, and between them they plot a surface, which then the program works out at each instant what is the efficiency of the chiller. So I won't spend much time on that, but this is important. Okay. Now you can see here there's a minimum part load ratio, a maximum part load ratio, an optimum part load ratio, and a minimum unloading ratio. Now these are important things for you to understand. When it says minimum part load ratio, it's telling you that you can use the chiller right down to 10% of its capacity. And actually that's not very true. At 10% of its capacity, it's working very inefficiently. And most practical engineers don't like to run their chillers that low. Okay. Using a control system, they will ensure that it doesn't unload to this value. The product suppliers will all tell you works fantastic at 10%. I would say exercise some caution when you do that. Okay. So if let's put it at 20%. 20% most modern chillers can work at without too much difficulty. So I'm going to put the minimum part load ratio and the minimum unloading ratio at 20%. So really the chiller can't run very stably and very efficiently when you are asking it to provide less than 20% of its capacity. Some of them do, but they have things like hot gas bypass, which actually make it less efficient. So why would you want to run a chiller at its most inefficient point when you've got 2 chillers in your plant room? Okay. So that's what I'm going to do. And this one is just called chiller for the present. I will say okay on it. So I've edited the loop. I've edited the chiller object as it is. Okay. And what I want to do before I go forward is also to look at the pump and possibly edit that and see what's going on there. Okay. So here's my chilled water loop supply pump. Okay. And I can edit that. And what I want to know is, because I've got a variable speed loop for the chilled water, the pump has to be a variable speed pump. You can't have one without the other. If the loop was constant volume, then the pump has to be constant volume as well. Okay. It'll auto size it for you, but the thing to watch out for is this design pump head. Okay. Now, for some reason, in the UK, they seem to think that this is all right. 20 kilopascals. We don't. I haven't seen too many designs that are that low. You need a really big pipe to do that. So typically about 200, so a factor of 10 increase on this is what I see in practice. Now you might need to speak to your mechanical designers and find out what they use. But I would suggest 200 kilopascals is a reasonable number. That's 200,000 pascals over here. Okay. Motor efficiency, I will leave at 90%. Okay. And this design flow rate minimum. Now that's something you may have to come back and reset at some point. Because again, you can't have the chilled water volume go down all the way to zero. You have to stop it somewhere at some minimum flow. That depends on the chiller. Typically, most chillers have got a limit to how low they can go. Typically, about 70% of their design volume is all that they can drop down to. And these are things that most modelers are not even aware of when they're doing that. So you hit the button, you get some numbers, and you go away and say, yeah, it's great. But in practice, you will never get these numbers unless you have looked at some of these things before. I'm going to leave the pump control at intermittent. It just means that when the loop is off, the pump is off. And I'm going to use the default pump curve. Essentially, it's just a linear curve. And in most instances, this is fine. Now, the reason I say this is fine is it's not the pump curve that you're interested in. It's the pump system curve, because the pump is pumping through a piping system. We haven't designed the piping system right now. We really don't know that unless somebody works through the number of bends and the length of pipe and the pressure drop across the chiller evaporator vessel and so on and so on and so forth. Okay, so typically using a linear curve is reasonably good conservative value. So I'm going to leave that over there. Now we'll go back to our chiller loop. We've now set the loop requirements, set the pump requirements. In most cases, the set point manager or the controller for the loop can be quite simple. Okay, and in this case, if I'm not wrong, it will simply say that, yeah, here you go. It's basically all the time the temperature is set to be 6 degrees centigrade, right? So basically, it's controlling to the fact that when required, it will provide 6 degrees centigrade water. Okay, so on the right hand side you can see that. Again, I would suggest that you write your own schedule, make this a temperature schedule instead of an on schedule, and leave it at 6. All the defaults you need to check to just be sure that it's working correctly, but for the present this will work. Okay, now let's go back. I'm going to the supply side of the loop. That's what we're interested in. We want to add a second chiller. If you look at the way this loop is put together, you can see that this pump is outside of the supply and return headers. Okay, but really when you have two chillers in a plant room, each chiller has got its own pump. For safety's sake, most engineers like that, so that when a chiller starts, its pump comes on first, maintains flow, then the compressor starts. So there's no chance of the compressor burning out. Okay. A lot of engineering here, I apologize, but it's good if you know that. So now what I'm going to do is I'm going to select that chiller. Okay. And I'm going to clone it. I've already decided what I want to do with it. If I clone it, it carries in everything along with it. So there's my clone object, and then I just click inside once and I put a second chiller somewhere close by. Okay. Now I need to do all the hydraulics, plumb it correctly as we call it, right? So I will escape out of that and I will select this pump. Okay, clone that pump, put it somewhere here, and that's fine. Then I need to move this pump out of here. Okay, so what I'll do is escape out of that and then delete this pump. Okay, right, and then delete this connecting branch. Right, now I can move the pump over there. And I need to rotate it so that it's in the right direction. Okay, one more time. Whoa. Okay. I want it to face the other way. Hang on. Models always don't behave the way you want them to. Ah, here we go. Perfect. So now I've done that. I can just connect it up. So if you've been looking at it, you can see that this pump is pumping through this chiller. I need to have another one. So let me now clone this pump. So it's easy enough for me to do that. Again, click somewhere once in the middle. Put it somewhere here. I needed to go through that. Okay, I'll put it here. And then try and see if I can rotate it. Otherwise, I'll just change the... Yeah, perfect. I want to move it just a little bit. A big monitor is good, so you can do that. Okay, it's a little bit out of sync, but that's okay. That's fine. Now it's the same pump. Okay, it'll auto size, but it's a variable speed pump and it's got the control characteristics that I want on it. So now I can connect this one and then I need to move it just a little bit. There you are. And connect this guy to the header. Okay, and connect that guy to that header. Now you can draw anywhere you like, it doesn't really care. But if you, and you can draw on top of lines, again, it doesn't care. Just to make it look nice, if you want, you can drop on top. As you add chillers, it'll keep giving you extras, so you can continuously add more bits and pieces to it. Okay. Now we've got the two chillers plumbed to the header and the to the supply and return headers, but we deleted this connection, so we got to put that connection back. Okay, so that connection here will give me the look. So supply return header, two chillers plumbed in parallel, each with its own pump. Now the second chiller is also water cooled, so I need to connect the cooling tower to it. Now if I was going to do a second cooling tower, I'd do something very similar. Clone the cooling tower, put a separate pump on each one. For today I don't think we'll have the time, so I'll just have one cooling tower and I'll connect that for you. So as before, the loop is broken up into a demand and a supply side loop. Okay, so if you look at the condenser side loop, you can see that. If I go to the demand side, then what you'll see is that the chiller is now demanding cold water from the cooling tower. It needs the cold water to operate in a cool way. And the condenser loop cooling tower is going to supply that water to the chiller. If I go to the demand side of the loop, it will tell me what can be connected. So if I use the connection tool over there, you can see the lines. I'm just going to connect it without making it look too pretty, but essentially it will do what I want it to do. Okay, so you can see I've drawn over the pipes and it doesn't really care. So I've connected the cooling tower up. Okay, now I will go back and examine the cooling tower and make sure that all the defaults are correct. If necessary, I will change some numbers, etc. But right now, 2 chillers plumbed to a cooling tower, it'll work. Okay. So if I save that and if I run that, now one thing I have to do, which I told you before, but I haven't done that. We need to know 2 things. One is, if you are sizing those chillers, what sizing ratio do you want? Do you want 2 equally sized chillers? Do you want one chiller to be slightly smaller than the other? Okay, so you have a low load chiller and a main chiller. So let's do that. Let's put one chiller as the low load chiller, give it 40% capacity, but the other one is a main chiller, give it 60% capacity. And then we will need to kind of guesstimate what is the total size of the chiller that we need. Okay. Now one way to do that is, and I did this before the class, so I kind of know what the numbers are. I ran a single chiller model and then I looked at the evaporator output. I think I might still have it on screen. Let me just see. Yeah, here we go. So this was what I ran previously, and you can see here chiller evaporative cooling rate. And if I look here, you can see that on one day it hit 700 kilowatts. All the days before that was 600, but on one particular day, the combination of solar radiation, the building loads, the ambient temperature, I think that day ambient temperature was around 40, but it wasn't the highest. Yeah, that's about 40 degrees centigrade. It must have been a combination of the solar radiation plus the ambient temperature, but possibly it was a Monday and it was the early morning peak, whatever. But that day it hit 700. So what I can do is I can take that 700, split it into a kind of 40-60 ratio. So about 250, 280 kilowatts and 420. So what I'll do is just make both slightly bigger than that, make them 240 and 500. Okay, let's say 250 and 500 kilowatts. That'll give me what I want. So there's a reason for doing that. I'll show you that. So I'm going to go to my 2 chillers. Okay, and what we'll do is this one, we'll call this the low load chiller. Okay, and I will put a sizing ratio of 0.4, or I can give it a size. So maybe what I can do is give it the size explicitly. So at this point I will say that this is 250,000, which is 250 kilowatts, and that's fine. And then call this chiller low load. Now why am I doing this? I'll show you in 1 minute. And then go to this one, edit that, call this chiller main, give it a size 500,000. Okay, and that's fine. Now the reason I need to do all this is because I need to now tell the loop how those 2 chillers should be operated. Okay, so when I edit the data for the loop, you really need to tell it when, during which range, which chiller should work. Okay, so I'm going to say that there are 3 load ranges. Okay, I have one operating scheme. It comes on at cooling load. I won't worry about the operation schedule. And the low load chiller will come on till the loop is say 250,000. That's what we sized it for. 250 kilowatts. It will come on from 0 to 250 kilowatts. Okay. Range number 2, I want the main chiller to come on first, and then it will work from when the building's load exceeds 250 kilowatts till the other chiller runs out of puff, 500 kilowatts. Okay, and then in the final range I will keep again main chiller as priority 1, low load chiller as priority 2, I need to switch that. Yeah, and then it will happen when the load exceeds 500,000 or 500 kilowatts up to 700. Okay, so hopefully you understood that. Okay, when the building's load is less than 250 kilowatts, the low load chiller will work. When it's between 250 kilowatts and 500 kilowatts, the main chiller will work. When it exceeds 500 kilowatts, then the low load chiller will come on again. So sometimes we call this swing chiller operation. So some chillers swing in, some chillers swing out, and they keep going on. Okay, if you don't do this, then your chiller numbers are rubbish. Okay, it will run a chiller as and when it pleases. If you have 2 equally sized chiller and both are prioritized, it might run 2 chillers flat out, and you will get double the amount of energy use. Sometimes you might get half the amount of energy use. It's confusing then. So this is much time it took me to just set up the loop operation, okay, for the chill water loop. Now similarly you have to do things to each of the other loops, and I won't spend too much time here doing that. But what we can do is, what's the time? Okay, I'll spend about 10 minutes and I will show you how to add a second air handling unit and go from there. Okay, that way then you guys will be kind of pretty much set for what you need to do. So if I go to the air loop, here we are, you can see what's going on here. It's easier if you do the editing before you clone it, so that whatever you have edited, that will be cloned in the next version. So if I look at this, yeah, that's all fine, nothing different about that. I'll just go inside the HU, have a look at that. So I've got a cooling coil, I've got a heating coil, there's a mixing box. I don't necessarily want 2 fans. I need a supply fan and a return fan, but I might say that the supply fan is sufficient, produces enough static. I don't need a separate return fan. In that case, I can go inside the HU and I can remove the recirculation fan. So I'll remove the extract fan. Now I can decide what kind of economy cycle I want. Okay, so if I put an economizer, I have a series of choices to make. So if I put a fixed dry bulb economizer, then it will give me options to control that. So what is the high limit for the economizer? When the air temperature goes beyond that high limit, it closes the economizer and then it just picks up minimum outside air. So you need to know your HVAC behind that, the thinking behind that. Okay, so there's a series of things here, you can have a look. If you want heat recovery options at the air handling unit, you can switch it on. So you can have a thermal wheel or a plate heat exchanger. whatever it is that you want to. You can provide the efficiencies and effectiveness, so it's either plate or rotary, so all these options are available for you. I'll remove that for the present, and I'll leave the default 25 degrees is okay. All right, so my AHU is set up, so I've removed the fan. I can work with that. I just need to look at my Setpoint manager, because when I clone it, I'll clone that as well. And because I'm using a VAV system, then only certain controllers are available for me. Okay, so you can decide how you want to set it up. We'll go on, instead of scheduled, I look for what's called warmest. Warmest means, in control terms, some people refer to it as a high select. So it means that the supply air temperature, the air handling unit will look at all the zones that it is serving, and then it will find out which zone has got the highest cooling load requirement. Then it will work out the supply air temperature to just meet that load, and it will supply air only at just that temperature. Okay, so all the other zones may require less cooling than the supply air temperature that's set there. That's when you have a VAV box, and the variable air volume box will then slowly close. For those other zones, it will control the volume. Okay, so we're getting pretty heavy into the mechanism for VAV system. And similarly, whichever system that you use, whether it's a radiant system or it's a chill beam system or it's a underfloor air delivery system, you will have to understand the thinking behind the system to be able to effectively get a reasonable outcome. Okay, now 11 to 16 is quite okay. Sometimes they go a bit higher. In Australia, we can actually include the heating coil performance in the AHU, and we might have 20, 29. So it will move the temperature as required to what is needed. So for heating, it will do that. This temperature range is good for a cooling only type system. So the maximum supply air temperature, let's say instead of 16, we can make it as high as 18. Okay, so that's what I've got. That's fine, and I'm going to leave it at that. And all I need to do on the air loop, and we did this last time, so I'll just very quickly at the HVAC system level. There we are. I will clone that object. So, and then I need to do the same again with. Now, why these things take time is because when you are copying that, you're not just copying a drawing, you're copying all the data behind it as well. So it does become, there's a lot of data that it's trying to copy as you move it. Where am I? Suppose I put a little bit somewhere here. Okay. Okay, there you are. Now, we have these two air loops. We have two zone groups. Okay, and if I was going to take the time, I would name each one, so I can have a perimeter zone group. So I would put, say, the east, the south, and the west on one group, and then I'd put the north and the internal on one group. Why? Because in the north in India you don't get a lot of sun. It's similar to an internal zone. Okay, but for the present I'll just connect it up and just make sure it works. So there's a fair bit of work for you to set it up. Let me go to air loop 1, and in the air loop 1, if I go to the demand side, it will allow me to connect. So So if I have plenums, I can put them there, but for the present I won't. I'll just assume that they are all ducted. So here's my air loop. And then I need to then hook all these coils up in the right places. Okay, so if you pull it up there, then for the chill water system I need to connect the coil. For the hot water system I need to connect these 4 coils. Okay, so let me do that. So I'll go to the chill water system, go to the demand side, and you can see here it's telling me that these can be connected. So I'm going to do that. As I said, I'm not making it very pretty, but effective. Okay, so I've connected the cooling coil. And similarly, if I go to the hot water loop, so that's the boiler, and you can see 2 connections are there. If I go to the demand side, it will show me that I can connect these options. So again, with the connector, very straightforward. Go there. The dark line goes into the, oops. There we are. And this guy goes to this one. And there's another additional coil here. That should do. Okay. So every time I connect, they'll give me one more. So I can keep adding bits and pieces here. Okay. Now, I haven't fully checked the air side, but I know the set point manager is correct and so on. The only thing I need to do is to make sure that the zones are correctly assigned. That's important. Okay. So this first one, let me just make sure. Yeah. So let's say that's air loop. That was the original loop. I will make sure that the zones that are connected to it are the perimeter zones. So I'll go to this first zone group, and I will release the ones that I want to put onto the other one. So the internal one and the north one on each floor, I'm going to release from here. Okay, so these are all the perimeter ones. And then on the other one, it will tell me add some zones there. So I will. And the ones that I released, I'm going to add over here. So zone group 1 is all the center zone type zones. Okay. And now I'm ready to run this model. So when I run this model, I should get, when I look in detail, I should get 2 chillers running. I should have 2 air handlers running, doing different zones. Okay. So how about we give it I'll give it a small run. I'll just do a month. It's quicker. So instead of a week, I'll just do all of June. So 1 to June has got 30 days. Okay, so I'll just run that. And you can go and select different kinds of output. And the more output you select, the more data you can get. So you will get the data broken down by chiller, by fan, by pump. You can get numbers for each of those outputs. And then you can look at the hourly outputs, and you will be able to see. In fact, the thing we might look at in the hourly outputs quickly is the two chillers, because we've scheduled the two chillers separately. You can kind of see how they work for each other, and then I'll stop. I don't need to load the results here. I will pick it up using the result viewer. Okay. While it's loading, I'll be back in 1 second. Okay, I'm back. So we've got the results here. So if I look at the numbers here, you can start to see cooling numbers, fan numbers, pump numbers, heat rejection numbers. They're all in electricity. That's what we're doing. If you go down, I haven't asked for too many bits and pieces, but you can actually start to ask for details. I've asked for boiler report. I think I've got a chiller report, hopefully. Yep. So there's a chiller low load report, and we have run it for the month of June. So it will give you the kilowatt hour, the peak load that it asked for, etc., etc., etc. There's a lot of data available for you. The main chiller will give you in the same way. You can get the outputs for cooling tower, for the fans over here, pumps over there. So all of that data is available for you when you do the runs. And very quickly, if I pick up the hourly outputs and have a look, it's a little bit of searching you need to do and sort of try and understand what it's giving us. But there are two numbers here that I'm interested in. One is the thermal energy produced by the chiller. So the evaporator gives you the cooling rate that it's using. So the low load chiller evaporator rate is that much, and the main chiller is that. Okay, so you can see when they are running. Now if I compare that to, if I plot the outside air temperature, there we go. I'll plot this on another graph. Then you can kind of see how it responds, you know. So you have possibly, that is a day when you have quite a high amount of chiller. These 3 days seem to be quite high. Both chillers are running quite a lot. Okay, so you can see this one, this chiller is running quite a lot. That's the bigger chiller, that's the smaller chiller. Okay, so you know, you can follow what's happening. You can put stack curves and all of that. If you wanted to, you can just put this into a CSV file and show what, if you stack one on top of the other, then you can see what the total amount of thermal energy the chiller is providing. And then if you're interested in the electrical output, it will give you that as well. I think there is a chiller electricity rate. I think there's also somewhere, if you ask for it, there are COPs and all kinds of things. So you can start looking for all the data. There's also, if you're really mad keen, there is a custom variables that you can turn on, which then plots the you know, the flow, the temperature, the humidity at every point on the HVAC system. That gets really quite complicated, and unless you're working in some really detailed HVAC scenario, I'd suggest you stay away from that. I think that should be as much as I want to do. I'll try and answer your questions here, and I can see very similar questions to what I get most of the time. So how is chiller selection option? Is it through COP only or Any option mentioned like reciprocating chiller, screw chiller, centrifugal? Okay, thank you. You do have models for many of them. So if you go to um, the chillers, what I showed you was a centrifugal chiller, right? But within Energy Plus, there's a series of chillers that are available to you. I think with reciprocating, we don't have too many options, but within centrifugal, which is the sort of main type of chiller that's used, there's a series of them. I would say the only thing around here is that I know that these chillers are maybe one generation older than the chillers that are being sold in the US today. I don't know if these ones are available in India or not, but you can have a look at them. If you know the sizes you want, you have quite a lot of options available. So centrifugals, screws, and some absorption chillers available to you. If you read the manual, you can pick up, which ones are the ones that you are looking for. If you want your own chiller, you can. You need to create the curves that are custom for that. There are some freeware tools available, and if somebody is really interested, I can provide a spreadsheet. But you need to get the manufacturer to bring you data in a specific way, which they can do. They need to run their software and generate these curve coefficients, and then you can use that. Okay. Now, is IPLV value of chiller any use in this HVAC sizing system? So that's again a very interesting question. When you talk about IPLV, it's a kind of COP. COP is a performance at a specific design condition. IPLV is a slightly more different kind of condition. So it says that there are 4 points on a standard curve, and then it takes an average of when the chiller is running at 25% for so much percentage of the time, 50% for so much percentage of the time, 75% for so much percentage, 100% at whatever, and then it gives you a value. Okay. Now you can compare two chillers and their IPLV ratios. However, that has no relationship to how your building is requiring cooling. Okay, because in a building you have a multiple chiller plant through. The building is asking for different kinds of load levels at different times, and the IPLV by itself doesn't really make too much use. An experienced engineer will look at the IPLV, look at I don't know how many of them do it, but I do. I'll run the model first to kind of look at how the cooling load varies across the year, and I'll even bin it to say that, okay, how many hours does it run, from 0 to 25% of the total plant capacity, 25 to 50% of total plant capacity, etc. And that gives me an idea of what I'm looking for. So on a couple of jobs, when I looked at it, from 75% to 100% of capacity, it was only using that plant for 4% of operating hours, which is a very inefficient use of plant. Okay, so how you select chillers can then come down to, can be informed by this kind of option. Okay. Hopefully I've answered both your questions over there.
There's one more question coming up.
Yeah. Yeah.
Is any option to consider redundancy or refrigeration load to reduce plant load, or any other tips that you
Okay,
can?
that's I was kind of saying that. I guess the easiest way to do that is if you run the model first without a detailed um, HVAC, but just the simple ideal HVAC, it will plot for you something called the district cooling load. Okay, and that shows you the variability of the thermal load across the whole year. Once you know that, then you can decide, uh, how to select a chiller combination to match that load. I think I might have a, let me just have a look. There is there's a presentation I used to have exactly about that. Let me just find it. Give me 1 second. So yeah, here we go. Okay. Yeah, so I'll just share this. Um, okay, now are you seeing, no, not the presentation. Let me just put the presentation on. Just let me know if you can see the presentation. Can you see the
Yes.
presentation?
Yeah.
Okay, so I'm sorry, let me find the right slides. Okay, yeah, I think this is, yeah. So when you run the model, now this is many years ago, so we were
Can you
using some
see?
other, yeah.
Yeah,
Can you see it
yeah.
now?
We weren't seeing the slide, but now we are. Yeah.
Yeah. So this is a model where I'm looking at the what is the demand on the chill water loop. Okay, and it's an hourly demand on the chill water loop, and it looks a bit weird because this is Australia. Winter is August, May, June, July, August. So cooling load is lowest here, and for us, February is the highest cooling load, and of course in India it's completely reversed, and June, July, August is your May, June, July, August is your highest cooling load. But anyway, but what it allows me to do is if I then put that into, take these numbers and stick it into an Excel sheet after doing a little bit of analysis, I can say how many hours of operation at what plant capacity range is happening. And this is what I was referring to a few minutes ago, right? So I can see that from 50% of the design capacity to 70% of the design capacity, that is where the chill water plant was running most of the time. Okay, so at that point, your chill water system needs to be very efficient. You still have quite a lot of hours, and this is Australia, remember, so it may not be the same for Bangalore or Delhi or Mumbai. It may be very different, but where is so from 0 to 25% of capacity, approximately a quarter of the time, 25 to 50% capacity, another quarter of the time, and then for the peak, only about 100 hours, between 75 and 100%. Okay. Obviously, your chiller selection needs to take this into account and make a efficient selection. When you talk about redundancy versus oversizing, this is what you want to look at. What percentage of the time does the chiller plant need to work at its maximum capacity? If it's only a few percent of the time, you have a couple of options. If your client is willing, you can have a negotiation with him to say, look, when the temperature outside gets over this value, then we won't be able to maintain strictly 24 degrees centigrade. It may go to 25 or it may go to 25 and a half. Are you okay with that? In that case, we can make your chill water plant much smaller. But if they are a kind of client who is not responsive to that, most bankers don't like their temperatures, moving up and down, in Australia anyway, then engineers tend to over design and have extra capacity for that. So that becomes not so much a technical issue, it becomes more a legal or a discussion arrangement. So that would be my uh, my my tip, I guess.
Yeah, so there's a question in the chat as well. So
Okay,
cooling tower performance impact chiller plant performance. So how to optimize the same?
very good. Thank you for that. I haven't looked at that condenser water loop at all, but you're absolutely right. Now, how does condenser water affect chiller performance? The colder water that you can give from the cooling tower, the more efficient the chiller becomes, okay, to a certain point. If you make your cooling tower water colder, then you can't use that water for reheat. So you have to kind of decide what is more priority, okay? But control strategies are available. You have a set point manager over here. If you edit the loop data, you have settings that you can work with. Um, so this is your basic loop data, and my design exit temperature is 29 degrees. My delta T across the loop is 5 degrees. So 29 to 34 degrees centigrade is what this one is designed to. Okay. Plant, now there's only one, so the plant operation loop doesn't really matter so much. But if there was more, then I can stagger the cooling tower. But what you can do is that you can actually, at the set point manager, you can decide what is the control strategy that you want to do for this one. So there are some options available. In this case, I'm following the outdoor wet bulb temperature, and there is a minimum temperature you can bring it down to and a delta T. Now these are not values that I would use, these are the defaults. Typically you don't want to go down much below 20. It's very difficult to do that, and your approach temperature will also be not 1.5, it may be 3 degrees to in practice. You need a really big tower to get a 1.5 degree approach temperature. So you need to understand some of these things before you start to put it, but all that is available to you. These are all the different options. There are five different controller types that are specific to cooling towers, so you can select that and select the appropriate subcontrol criteria. Okay.
Right. Yeah. Thanks, PC. I think that was the last question. But I do have something like a question for you. I mean, which is very relevant for a team where there's a multidisciplinary team where there's architecture students and engineering students. So, if a model specifically for a complex system, if it is designed by the engineer in their team, would you recommend you know separately working somebody like the engineer designing the system itself, and then finally exporting and then importing? Would you recommend that, or you would?
Yeah. I think it makes a lot of sense that you have the architects optimize the fabric.
Mm.
And then once the fabric has been optimized, the cooling load for the fabric has been optimized, for which you don't need the detailed design,
Right.
HVAC design. Then the mechanical engineer, see, you also need to make some decisions about what kind of system is appropriate in this climate for this use, those kind of things. All those discussions probably need to be had with the mechanical engineer. And then with the mechanical engineer, which AHUs are going to serve which zones. Okay. What's the control criteria for the chill water loop, the air loop, condenser loop? These are all questions that should be discussed with the modeling team, and then the modeling team may have to put it together. You can't, unfortunately, um, export and import, as you've said. I wish that were possible. That's the holy grail of energy simulation everywhere in the world, and nobody's really managed to crack
Right.
that. But you can, the architectural model can be given to the mechanical engineer, and the mechanical engineer can certainly work on that model.
So, Amanda, one thing I'd like to add here, in the structure of Solar Decathlon India teams, it's quite likely that even if they have a mechanical engineering student, the student won't have the level of design experience that's needed for, making decisions on zones and controls and all the components. So what I would recommend for such teams is that even if you have a mechanical engineering student, either you have a mechanical engineering professor who can guide you, or you bring an industry partner in, somebody who's a practicing mechanical engineer, and go through these kinds of decisions with them so that your systems become robust. And then you can, then who is the engineer who's modeling it actually has the kind of information that's needed to be able to build a model.
Right. Yeah.
Yeah. And also, my other piece of advice would be that to be able to model, the very sophisticated systems takes a very long time to get it right. You're better simplifying the approach, but making it more robust and slightly conservative so that those numbers will actually be available to you in practice. When you go and take the metered readings, and we've seen that in practice, we've done so many buildings, we kind of know by the time we look at somebody else's simulation or our own simulations that these numbers are achievable and reasonable. We take fairly robust conservative assumptions, not too conservative. You want to be able to show that if you've made a particular control strategy happen, then that there is some benefit from that, but it does take a little bit of experience to get there. If you choose a fairly common system configuration that the practicing engineer is good with, he'll be able to give many of these check numbers quite easily.
Right. Yeah. So there's one last question. I don't know if we should take it down because, but so the question is from Professor Gunjan. For smaller capacity plant, generally use fan coil unit rather than VAV box. Is fan coil selection option available? I think it is.
Absolutely. Let me just share my screen. So at the zone, see what you are doing then is that at the zone level, you are selecting some componentry, right? So what you can do is that at the zone level, instead of using your VAV with reheat, you can pick other zone level systems. So you can get fan coil units, packaged heat pumps, anything you like. So in fact, the kind of equipment that's available in Energy Plus is very vast. You can pick pretty much anything you want, and the controls that are appropriate to that. And of course, for the fan coil unit, if I pick that one, then I put it in here. You can then decide how the outside air is going to come. So in this case, there's no outside air. You can switch on outside air. You can connect the cooling coil to the chilled water system, the hot water coil to the boiler system, so on. It's quite flexible that way. Yeah, and if you don't want the hot water system, you can either schedule it off, or you can put an electrical system and just turn it off. No problem there.
Okay. All right. Thanks, PC. That was the last question. And also, since this is the last simulation webinar, before we end or close this webinar, would you like to add something, or even Prasad, if you want to add something?
I might add that there was the one person asking a lot of questions. Who is that? If I, yeah.
Yeah, it's from Professor Gunjan Kumar. Yeah.
Oh, right. Okay. Well, Professor Kumar, if you want to reach out, I'd be very interested. I'm very interested to know anyone who is interested in air conditioning. I have not found too many educators who are that keen on that. So, um, happy to
Right.
have a talk. Yeah.
Thank you, PC. These webinars have been really useful. They're more like detailed workshops, and the level of detail that you've gone into is quite amazing. So I hope that our participants are able to make the best use of the amount of knowledge that you've been able to give on this. I'm pretty sure that they'll have to go and look at the recordings, over and over again to be able to understand so many important and detailed information that's available. So thanks a lot from Solar Decathlon India.
Thank you. And I hope the participants have found it useful.
Right. Yeah. Thank you, PC. Yeah, I mean, definitely it was very informative. You kind of also added things like that might work practically or might not work. So it was really good. And yeah, it was an honor to moderate your webinars and learn many new things as well. Yeah, and thank you to all the attendees who have joined today. Thank you once again.